One morning, your files open normally. By afternoon, they refuse to. A text file appears on your desktop calm, almost polite, telling you your documents, photos, and work are securely encrypted and can only be recovered for a fee. Nothing looks physically destroyed, yet everything is functionally gone. That's the core trick behind ransomware. It doesn't break your data. It turns it into something you can still see, but no longer understand. Welcome to BlueHat Cybersec Academy. This breakdown focuses on file encryption tactics used in ransomware, but not from a surface-level "what is malware" angle. Instead, it's a structural look at how attackers actually lock data, why the method works so reliably, and where the real assumptions in defense start to fail. And as we go through this, keep one question in your mind. How do you defend something that is mathematically intact, but practically unreachable? Ransomware is often misunderstood as destructive malware, but that's incorrect in most modern cases. The attacker's goal is not to erase data, but to preserve it while denying access. And that distinction is everything, because it explains why encryption is the core mechanism instead of simple deletion or corruption. From the attacker's perspective, encryption creates three outcomes at the same time. First, the files remain intact, which gives proof that the data still exists and can be leveraged. Second, the victim experiences psychological pressure because the data is still visible but unusable. And third, recovery becomes mathematically difficult without the correct keys. In simple terms, this is extortion built on cryptography, not destruction through force. Now, before encryption even begins, the malware doesn't just randomly start locking files. It actually performs a structured reconnaissance phase. It scans mounted drives and network shares. It enumerates file types like documents, databases, archives, and images, and it deliberately avoids system-critical files at first so the machine keeps running. At the same time, it prioritizes high-value directories such as business data, backups, and user profiles. This selective targeting is intentional. If ransomware encrypted everything blindly, systems would often crash too early, which would reduce both impact and the chances of payment. So most modern ransomware families maintain what you can think of as internal logic rules. They whitelist system directories they avoid, and they blacklist file types that are not worth encrypting, all to keep the system usable long enough for the ransom message to land. At this point, you should already notice something important. This is not chaos. It's controlled execution. Once the target set is defined, the next layer is the encryption model itself, and this is where most misconceptions appear. Many people assume ransomware uses a single encryption algorithm to lock everything, but in reality, most modern strains use what's known as a hybrid cryptographic system. Here's how that works in practice. First, there is symmetric encryption for speed. Each file is encrypted using a fast algorithm like AES, or Advanced Encryption Standard. The reason for this is simple. It handles large files efficiently, it minimizes CPU overhead, and it allows rapid encryption across entire drives without slowing the system down too obviously. Then, there is asymmetric encryption for key protection. The symmetric keys, which are used per file or per session, are then encrypted using the attacker's public key, usually based on RSA or ECC systems. This second layer exists for one critical reason. It ensures that the decryption key never exists in a reusable form on the victim's machine. And even if someone reverse engineers the malware binary completely, the attacker's private key is still required to undo the encryption. So now ask yourself a serious question. If the algorithm is known and the process is visible, what exactly do you attack? Because the weakness is not in the encryption itself. Now moving deeper, each infection typically generates a very specific key structure. You often see a unique encryption key per file or per victim, a session-specific key exchange mechanism, and a securely stored public key embedded inside the malware or fetched from a command and control server. In more advanced variants, this process becomes even more strict. Keys are generated on the fly, immediately encrypted, transmitted to attacker-controlled infrastructure, and never stored locally in plaintext. This is where ransomware becomes structurally asymmetric in power. The victim still has all the encrypted data, but the ability to reverse it exists only in infrastructure they cannot access. And here's the uncomfortable thought that follows that. If the key never existed in a recoverable form on your system, what does recovery even mean at that point? Now, once encryption begins, ransomware shifts into another critical phase, what you can think of as the point of no return mechanism. This is where it actively removes recovery options before or during encryption. It deletes shadow copies through the Windows Volume Shadow Copy service. It disables recovery utilities. It targets backup software processes, and if backups are accessible, it encrypts them as well. It also terminates database services and file locking processes to ensure files are not in use in ways that could block encryption. The logic behind all of this is very straightforward. If recovery paths still exist, then the ransom loses leverage. So this stage is not random damage. It is the strategic elimination of redundancy. At this point, something else becomes obvious. Most systems don't fail because encryption is too strong. They fail because recovery paths are deliberately dismantled. Then comes the constant balancing act between speed and stealth. Ransomware developers are always trying to encrypt fast enough to cause maximum damage, while staying quiet enough to avoid early detection. To do this, many variants use multi-threading, so multiple files are encrypted simultaneously. They limit CPU spikes so the system doesn't appear abnormal. They often operate during off-peak hours, sometimes checking system time before executing, and they may delay execution using sleep timers or staged triggers so initial infection doesn't immediately reveal itself. At this stage, ransomware stops looking like random malicious code and starts looking like a controlled industrial process, tuned for timing, efficiency, and concealment. And that raises another question. If something is designed to look normal while doing damage, how exactly do you detect it in time? From a purely mathematical standpoint, modern ransomware encryption is effectively not breakable in any practical sense. The reasons are structural rather than theoretical. AES 256 has an astronomically large key space. RSA and ECC rely on hard computational problems that have no known efficient solutions. There are no scalable shortcuts for properly implemented systems, and offline brute force is not just difficult, it is economically and computationally unrealistic. So when recovery does happen, it is almost never because encryption was broken. It happens because of something else entirely. It comes down to implementation failures, key leakage, usable backups, or law enforcement access to attacker infrastructure. And that leads to an important conclusion. Security failures in the real world rarely come from mathematical weakness. They come from operational mistakes. Even with strong cryptography, ransomware often fails due to implementation errors. Poor random number generation for keys, reused keys across victims, incomplete encryption routines that leave parts of files intact, debug code accidentally left in production builds, or misconfigured command and control servers can all create cracks in what is otherwise strong encryption. Ironically, most successful decryptions in real incidents come from these kinds of flaws, not from breaking cryptography itself. So if the math is strong, the real question becomes, where is the real battlefield? Is it in algorithms or in execution errors? From a defensive perspective, if encryption is mathematically sound, you cannot rely on undoing it after the fact. Defense has to operate before or during execution. That means immutable offline backups that are not connected to the system, network segmentation to limit lateral movement, behavior-based detection that watches for rapid file modification patterns, least privilege access controls that reduce exposure, and monitoring for shadow copy deletion attempts that often signal early encryption stages. And here is the uncomfortable truth that ties everything together. Once encryption completes properly, recovery is no longer a security problem. It becomes a data availability problem, and that can only be solved by preparation done beforehand. So the real question is not whether encrypted data can be recovered later. The real question is whether the system was ever designed to survive the moment encryption begins. And finally, ransomware doesn't actually exploit a software bug first. It exploits a much deeper assumption, the assumption that data remains accessible simply because it exists. Encryption breaks that assumption cleanly. It leaves systems intact, files visible, and users fully aware of what they've lost access to, which creates pressure without destruction. And that is why file encryption remains the most effective weapon in modern ransomware. It turns mathematics into leverage and access into negotiation. Now here's your challenge for the comments, and I want you to think carefully before answering. First question: why do ransomware attacks use both symmetric and asymmetric encryption instead of relying on just one? Second question: what is the real purpose of deleting shadow copies before encryption actually begins? Third question: if encryption itself is not realistically breakable, where do most real-world ransomware failures actually happen? And fourth question: in your opinion, which matters more in defense against ransomware, prevention or recovery? And why? Write your answers in the comments and compare them with others watching. And if you want to keep building this kind of structured understanding of real malware behavior, not surface-level definitions, then stay with the Malware Encyclopedia playlist. If this helped you see ransomware as a system rather than just an attack, then like, share, and subscribe so you don't miss the next breakdown in this series.